Hey everybody, limits in differential calculus. Day number 1, today's topic is evaluating one and two-sided limits, handling indeterminate forms, laws of some limits, and then the limit definition of the derivative. Let's get it started. All right, your number 1 avenue of approach and first strategy should always be direct substitution. What a limit is basically a y value. So as a function approaches a certain x value, the limit is asking you to evaluate what y value the function would be approaching. So the function x plus 5 over 9 as x approaches 3, direct substitution would tell us that we are going to substitute a 3 in for x. So we would get 3 plus 5 over 9. So this limit evaluates to 8/9. If you ever get a number, finite number over another finite number, like we did here in number 1, you're done. That's the y value that function approaches as x approaches 3. That's great. Okay, let's look at a more general case. Number 2. The limit as x approaches a of the function x squared minus a squared over x plus 3. Well, if I plug in an a everywhere I see an x squared, or an x, excuse me, I get a squared minus a squared over a plus 3. Let's assume that a is a real number. So a is in the real number set. Then I would get a squared minus a squared, which is 0, over a plus 3. I don't know what that is, but I know it's a real number. Let's say that a is not equal to 0. Okay. And a is, well, we'll say a is also not equal to -3, because that would be a problem here as well. So I'm kind of making that up as I go. But if you get 0 over a number, that's also great, right? You get 0. So you'd be done. Work is complete. Let's look at number 3. Limit as x approaches pi over 2 of sine of x over 2x minus pi. All right, so sine of x, sine of pi over 2, okay, over 2 times pi over 2 minus pi. All right, so this will evaluate to 1 over pi minus pi, which is 0. Okay, that means that this limit does not exist. So if you get a number over 0, even though it doesn't exist, that's good, because now you have a definitive answer. Okay, let's look at the 4th example. So up until this case here, if we got a number over a number, 0 over a number, or a number over a 0, we were complete. All work was finished. But let's look at number 4. Limit as x approaches -5 of x squared minus 25 over x plus 5. Well, that would be -5 squared minus 25 over -5 plus 5. Okay, this gives us 25 minus 25, which is 0, over -5 plus 5, which is also 0. This is not good. Okay, it looks like a little tear on that eye there. Okay, not good. I love that. I don't know, that kind of looks like a somewhat happy face. I don't know. But this is in an indeterminate form. Indeterminate form. And the 2 indeterminate forms we're going to look at today are the form 0 over 0, as well as positive or negative infinity over infinity. Okay? So these 2 indeterminate forms we have ways of dealing with, but this means that you have more work to do. There's more work to do. You're not done yet, so you're kind of like me. Okay, I guess we got to do some more work. So let's do a few examples. Okay, so the indeterminate form 0 over 0 can be dealt with in a lot of ways, but we're going to look at 3 ways. The first way is called factor and reduce. So what I'm going to do is I'm going to factor anything possible here. So I'm not going to do all the work here, but I would get a form of 0 over 0 here. If you plug in a 2, you'd get 4 minus 4 over 2 minus 2. Okay, so what I'm going to do is I'm going to factor, leaving the limit notation, not evaluating left yet. I'm going to factor x plus 2, x minus 2, and I leave the denominator as is. What you'll notice is that from pre-calc, you should notice that there's a hole in the graph at x equals 2. Therefore, this would be equivalent to the limit as x approaches 2 of x plus 2. So that function actually is a line, the line x plus 2, just with a hole at positive 2. So here's a graph of x squared minus 4 over x plus 2. X minus 2. X minus 2. Okay, it'd be a graph of x plus 2, and there'd be a hole at positive 2. All right, so here's the graph of x plus 2 with a hole in the graph at x equals 2. So there's a discontinuity there. It's an attempt to fool us, right? It's not truly a line. It's a line with a gap in it. So we deal with this by factoring, reducing, and then evaluating. So the limit as x approaches 2 of x plus 2 will be 2 plus 2. Right? I sub this 2 in for x, and I get 4. Okay. In some cases, you might still get a number over 0, then you know it doesn't exist, or you might get 0 over a number, then your limit is 0. Right? That's just your y value that you'd be approaching. So in this case, we're approaching 4. Okay, our second method is called clearing fractions. You'll know when to clear fractions because you'll see it. It's evident here that I'm going to clear fractions. Okay, if I were to plug in m, I would get 1 over m minus 1 over m, right? 1 over m minus 1 over m minus m. That's going to clearly be 0 over 0. So what you're going to want to do is we're going to want to clear the fractions here. And what I mean by that is I want to get rid of the fractions in the numerator. So I'm going to multiply both the top and the bottom by x and m. That'll clear those fractions there. That means I also have to multiply down below. So this is equivalent to multiplying by 1 because I'm multiplying by x and m on the top and the bottom. Therefore, if m is a constant, limit as x approaches m, okay, we can see that the numerator would become m minus x, right? Because as I distribute this to 1 over x, I would get m. And as I distribute it to 1 over m, I would get x. And in the denominator, I would get x times m times x minus m. Now you might think, well, I don't really see where to go from there, but if we rearrange slightly, I could take out a negative 1, and I would get x minus m here on the numerator. I could do the same in the denominator. I'm choosing to do so in the numerator. So you can see that there's a hole here. There's a discontinuity at x equals m. Thus, I can reduce, and I would get negative 1 over x times m. Now I'm going to evaluate now, which means I'm going to plug in an m for x. That means my limit would be negative 1 over m times m. There's our limit. Very good. Okay, the third method here is called conjugate and reduce. Okay, so the conjugate will happen anywhere that you see a radical. Okay, so typically you'll see a binomial. So in this case, we have the radical x plus 6 minus 3. So in order to work with this, clearly I'd get 0 over 0. So the square root of 9 minus 3 would be 0. And 4 times 3, which is 12, minus 12 would also be 0. So I'm going to multiply the top and the bottom by the conjugate of the top. The conjugate of the top, in this case, where the radical shows up, is square root of x plus 6 plus 3. Right? So this plus right here is the opposite sign of the minus right there. All right, I'm going to do the same thing in the denominator. we'll get an equivalent expression. Okay, when you multiply conjugates, this is really nice. You are technically foiling, but the outside and inside terms are reducing. They end up being the same with opposite signs. So all I have to do is multiply the first term. So square root of x plus 6 times square root of x plus 6 is x plus 6. And negative 3 times a positive 3 is a negative 9. So that's the numerator. The denominator is going to be kind of messy. But I'll have 4x minus 12 times that conjugate, square root of x plus 6 plus 3. And we'll see something happen here. It's pretty nice. Okay, so I'm going to have the limit as x approaches 3 of x minus 3, right? I took the positive 6 and negative 9. And I'm going to actually factor out a 4 here, which will leave me with x minus 3 again, and the conjugate from the numerator earlier. All right, so you're going to see then that discontinuity disappears. So this will be the limit as x approaches 3 of 1 over 4 times the quantity square root of x plus 6 plus 3. So when we evaluate, I plug in a 3 for x, which makes this 1 over 4 times the square root of 9 plus 3, which is 6. So our answer, when we evaluate, is 1 over 24. All right, so let's move on to the other indeterminate form, infinity over infinity. Okay, the indeterminate form, infinity over infinity, can be dealt with in many ways as well. Here's one way, and I'm going to do 2 examples with the same method. Okay, first thing I'm going to do is I'm going to make sure that both the numerator and denominator are in standard form. So x squared minus x minus 6. Notice that our limit is as x goes to infinity in this case. And then I'm going to distribute in the denominator, which will give me 2x cubed minus 5 times 2 is 10x. Okay, so how do we evaluate this? Because clearly the numerator will go to infinity, and so will the denominator. So what we do is we use a method where we're going to divide all terms by the largest power. Okay, so what I'm going to do here is take x squared minus x. I'm going to spread these out a little bit and let you see this. 2x cubed minus 10x. And I'm going to find the largest power. The largest power is right here. So I'm going to divide everything by x cubed. Okay, when I divide by x cubed, all right, I'm technically dividing both the numerator and denominator by the same value, therefore it's an equivalent statement. So I will get, as I reduce, 1 over x minus 1 over x squared. Can't reduce the third part. Denominator, I'm going to get 2 minus, that'll be 10 over x squared. Now, think about this. As x goes to infinity, that's going to go to 0. As x goes to infinity, that's also going to go to 0. As x goes to infinity, that will also go to 0. So we see that the numerator is going to go to 0. Let's look at the denominator. Well, I'm going to have a 2. And then this term will also go to 0 as x goes to infinity. So what I'll have, excuse me, that should have been a minus there, is I'm going to end up evaluating this to 0 over 2. And 0 over a number is great because that means the limit equals 0. Let's look at the next part. Okay, I see that I have kind of an odd setup here due to the square root containing the entire function or expression. So I'm going to have the square root. Actually, I'm going to do this. This is going to be cool. All right, this is a property that you're going to learn in a minute. But if I have the limit as x approaches infinity of the square root of a function, I can actually take the square root of the limit and get the same answer. So I would have x squared over 3x plus 9. Okay, so I'm going to do exactly what I did before. I'm going to take and divide everything by the highest power. So that would be x squared over the highest power x squared divided by 3x plus 9 also over x squared and x squared. All right, so as I look at this, as this will reduce to 1, so I'll have limit as x approaches infinity of 1 over, this will be 3 over x plus 9 over x squared, square root of all of that. Okay, so as x goes to infinity, this will go to the square root of 1 over 0 plus 0, right? As x goes to infinity, 3 over x goes to 0. Same thing there. So I'll have the square root of 1 over 0. And a number over 0 is great because we know that it will not exist, right? Okay, so a couple of different ways, right? These two limits, one of them exists and it's 0. The other one does not exist. That method I would call, it doesn't really have a name, but I would say dividing by the highest power. And this work specifically is with polynomials. We'll talk about other methods with other functions later. Okay, let's move on to the next slide. Okay, so the definition of a limit is given that a is some real number. The limit as x approaches a of f of x exists if and only if the limit coming from the left, right, this notation right here, is the limit as x approaches a from the left of f of x is equal to the limit as x approaches a from the right of f of x. I mean, that makes sense, right? If I have a graph of f of x, and here's a, right? If the function coming from the left side and the function coming from the right side don't agree, right, then we got an issue, right? Then the limit doesn't exist. The limit could exist from the left and it could exist from the right, but it won't exist, right, at that value. Now here would be an example of, you know, this working out. From the right, you can see, and from the left, you can see that they are, as x approaches a, equal to each other. Okay, so determine if the below limits exist. Describe why or why not. So what I want to do is I want to take the limit as x approaches 0 from the left and the limit as x approaches 0 from the right for this function. I'm going to call this thing f of x cosine of x over square root of x. Now, if you're thinking right, you could think graphically. Okay, from the right, what's the cosine of 0? Well, the cosine of 0 is 1. And what's the square root of 0 coming from the right? Well, that's 0. Okay, so I'd like to say it does not exist. The limit does not exist. Now, there's a couple reasons why the limit doesn't exist here. One of them is that, well, clearly 1 over 0 isn't going to exist, but as we approach from the left of 0, we're going to get the same thing, but we're going to have an issue here because the limit as x approaches 0 from the left of square root of x, that's not possible. That does not exist, and the reason is because the graph doesn't exist there. Right? The square root of x doesn't exist over here coming from the left. So, two reasons, right? The limit as x approaches 0 of f of x does not exist. One of which is because the limit as x approaches 0 from the left does not equal the limit as x approaches 0 from the right. The other reason is because the limit as x approaches 0 from the left of square root of x does not exist. Therefore, we got problems. Okay, let's look at number 2. Let's look at f of t. This is a piecewise function. I want to know if the limit as t approaches -2 of f of t exists. Okay, so as I look at -2, I don't need this first stem of the piecewise function, right? Because that's not applicable to where x equals, or t equals -2. I want to see if these two functions, the limit as t approaches -2 from the left of f of t, which will apply to this part of the piecewise function, and the limit as t approaches -2 of f of t from the right are equal. I want to know, are those two equal? So let's try this. So this limit here will be the limit as t approaches 2 from the left of f of t, which will be t plus 19. Okay, so what will that equal? As I plug in a 2, that'll equal 21. All right, now as I look at the limit from the right-hand side, that'll be the limit as t approaches -2. Ooh, I'm sorry, it was supposed to be a -2. From the left, so this would have been a 17. Messed that one up. All right, of t cubed over t plus 9. So if I plug in a -2, I'm going to get -8 over 7. Okay, so the limit as t approaches -2 of f of t does not exist. And the reason why is because the limit from the left of -2 of f of t is not equal to the limit as t approaches -2 from the right of f of t. Okay, let's see if maybe we can get one that works. Okay, so we're going to take the limit as t approaches, oops, that should be x approaches, pi over 2 of f of x. So I'm going to test the left side. Here's the left side. And here is the right side. You can tell left and right based on the inequality. So the limit as t approaches pi over 2 from the left of f of t is going to be equal to the limit as t approaches pi over 2 of sine of x. Gosh, these need to be x's. I got problems. Got problems, folks. It's getting late. Haven't done my push-ups. All right, so what will that equal? Actually, I have done my push-ups. So the sine of pi over 2 equals 1. All right, let's work the other side. Limit as x approaches pi over 2 from the right of, not sine of x, that would be f of x would be equal to the limit as x approaches pi over 2 from the right of 2x over pi. What would that equal? Well, that'd be 2 times pi over 2 divided by pi. What we get is pi over pi, which is 1. Therefore, the limit as x approaches pi over 2 of f of x is equal to 1. Awesome. Okay, we got a couple slides left. Let's get into some laws, and then we'll look at why we even care about limits, and it's actually pretty cool. Okay, some laws, you guys. Limit laws, these are useful. Okay, let's assume the limit as x approaches a of f of x is L, and the limit as x approaches a of g of x is M, where a, c, L, m, and n are real numbers. Okay, we're going to use these constant values. Okay, this is the constant rule. If I've got constant times f of x, that limit will just be the constant times the limit. Okay, we got the addition rule here. We got the subtraction rule, multiplication rule, division rule, power rule, and then rational power rule. Just look them over, and you'll see some examples of how to use those in homework problems and other HL examples. So let's get to the why. This is my favorite part. Okay, so maybe You've wondered why limits are so important. I hate limits. Why would I do limits? They're dumb. Just get me to the shortcuts. Well, here's why they're important. Because they apply directly to derivatives and to slopes. Okay, so let's say I wanted to find the slope of the secant line from there to there. Well, slope is pretty easy to work with, right? So if this is x, then this would be f of x. And if this is x plus h, this would be f of x plus h. So the slope, right, we could find by using y minus y, so f of x plus h minus f of x over x plus h minus x. Cool. So the slope, let me just simplify real quick, would be f of x plus h minus f of x all over h. You've probably seen this. It's been called the difference quotient. Okay. So what would happen if I started to compress this interval and I brought x plus h closer and closer and closer to x? Well, the closer that I get to x, right, as I shrink h, what am I doing? The slope is getting closer and closer to the slope at the exact value, the exact slope at x. So if I take the limit as h approaches 0 of the difference quotient, this is equal to the slope or the derivative at x. Okay, represented, to make sure we can make this very clear, the instantaneous rate of change of f of x, the derivative of f at x, is equal to the limit as h approaches 0 of the difference quotient. It's awesome. Okay, that's the first form for the limit definition of the derivative. All right. The other form, let's look over here. All right, let's go to a different color. Let's do black. Okay. Here's I found the slope between these 2 points. You can see I'm doing something very similar. This would be f of x. This would be f of a. So the slope of the secant line between the two would be f of x minus f of a, which is y minus y, over x minus x, x minus a. All right, so what if I crept x back to a? And I'd start getting these secant lines that would approach, as I get to this point, would approach the instantaneous rate of change at a, right? That's the slope at a, or at least approaching it. So the limit as x approaches a of f of x minus f of a over x minus a is equal to the derivative of f at a. Okay, guys, I mean, some cool stuff. We're going to go through, I'll make another video on, when we get to differentiability, on finding the derivatives of some basic functions using the limit definition of the derivative. We're going to evaluate limits to show, right, that if f of x equals cosine x, we're going to use these limits and evaluating these limits to show that the derivative is equal to the negative sine x. Okay, cool. That's it for day number 1 on limits, indeterminate forms, and limit definition of the derivative. Have a great day. See you in day 2.